Alright, so everybody is able to hear me, hopefully everyone. Alright, so let us start today's lecture on wireless communications. What we have done so far is we have been trying to look at the bit error rate of a wireless communication system, and we did that last time. What we did was we were looking at the first we looked at the bit error rate of a digital communication system, and we said the bit error rate of a digital communication system, that is given as the bit error rate of an AWGN channel or a conventional digital communication system. We said that is equal to Q of square root of SNR, which can be approximated as half e to the power of minus half SN. Fine. And on the other hand, for a wireless communication system, for a wireless communication channel, we said the bit error rate is, let me just write it down, we said bit error rate for wireless relay fading channel, the bit error rate is given as that is half 1 over 1 plus half SNR, which is approximately equal to 1 over SNR. Right, and we also, so this is basically we are looking at the bit error rate. Also known as BER. And we also said the following thing, we also said, for instance, in AWGN, if we want 10 to the power of minus 6 bit error rate, SNR required is equal to, does anyone remember what is the SNR required in an AWGN channel for a bit error rate 10 to the power of minus 6? That is approximately, if I remember it correctly, it is approximately around 14 dB, right? Approximately around 14 dB. I think exactly it was 14.19 dB or something. I don't remember it exactly. However, in a wireless communication system, that is, if I look at a wireless communication system, we looked at this. What is the 10 to the power of minus 6 bit error rate? What is the SNR required? Does anyone remember? We calculated the SNR required. What is the SNR required in a wireless communication system for a bit error rate of 10 to the power of minus 6? Can someone answer on the chat window? What is the SNR required in a wireless communication system for a bit error rate of 10 to the power of minus 6? That is approximately 60 dB, right? Correct? PSG, I am getting the answer. Yeah, 60 dB. That is because if 1 over, let me just briefly illustrate the calculation. If 1 over SNR equals 10 to the power of minus 6, then SNR equals 10 to the power of 6 implies, if I look at it in dB, it is 60 dB, 60 dB of the dBs of SNR that is required. So why is a larger, and if you can see look at the difference between these two, in AWGN you need 14 dB, but here you need 60 dB in a in this thing in a wireless. So it's a very high SNR is required in a wireless communication system, which means a much larger transmit power is required. In fact, how large? Remember, this is in logarithmic scale. So basically it is 16 minus 14 dB, that is basically 45 dB approximately. So we are saying approximately for same noise power approximately 45 dB more transmit power is required in wireless. 45 dB means 10 to the power of 4.5. So you need 10 to the power of 4.5 times the power of a wireline communication system. And why is this happening? We said the main reason is because in an AWGN, if you look at this, in an AWGN scenario, the bit error rate is decreasing exponentially. In AWGN channel, bit error rate decreases. It decreases exponentially. However, in a wireless relay fading channel, it is only decreasing as 1 over SNR, sort of inverse linear in SNR. So it's not decreasing exponentially. This is a very slow decrease compared to a, in fact, if you plot the bit error rate, if you plot the bit error rate of AWGN versus relay fading scenario, it is going to look as follows. That is, if I have this axis, AWGN bit error rate decreases very sharply, but for relay fading it only decreases very slowly. So this is a curve for, this is the AWGN and this is for relay. The bit error rate of relay fading channel or a wireless fading channel decreases much more slowly corresponding to compared to an AWGN channel. Now why is this happening? Let us understand this a little bit. What is the reason for this poor performance of the wireless fading channel? What is the, what is the reason for the high bit error rate of wireless? What is the reason for the high bit error rate of the wireless relay fading channel? Right, and this can be explained by something known as the deep fade. This arises due to the, this arises, that is the poor bit error rate performance of the relay fading channel arises due to the deep fade events in wireless channel. That is, this arises due to the deep fade event in a wireless. Now what do we mean by a deep fade? What is the deep fade? So to understand what is the result for the poor performance, reason for the poor performance of the bit error rate of a wireless communication system, we have to understand the properties of a deep fade. Now what is a deep fade? What causes a deep fade, and what is this phenomenon of deep fade, and how does it affect the bit error rate? So I will explain. So in this lecture I'm going to explain, that is in the next couple of minutes I'm going to explain basically what is a deep fade event and how does it affect the bit error rate performance of a wireless communication system. So see, we have a wireless communication system. We have y, the received signal, is equal to hx plus n. right? So we have y is equal to hx plus n. Now we said already that this is the, in the wireless communication system, we have, this is the signal part, and this is the noise part. This is the signal part, hx is the signal part, n is the noise part, right? So y equals hx plus n, we have both the signal and the and the and the noise. Now therefore, what happens when you have the signal and the noise? What is the signal power? So I have signal power is equal to expected value of magnitude of hx square is equal to expected, is equal to signal power is equal to, not expected value, let me calculate the instantaneous received signal power is equal to mod h square into expected value of magnitude x square. This is equal to magnitude h square into p equal to g times p. What this is saying is simple. We calculated this yesterday. This is basically saying that if the transmitted power is p, and if the gain of power gain of the wireless channel, that is magnitude h square, is g, then the received power is equal to g times p. That is, received power equals transmitted power times channel gain. So the received power is equal to the transmitted power times the channel gain, which is equal to E times P. I'm getting a question regarding the impact of scattering and diffraction. That is what we said. Scattering and diffraction causes the fading, and that fading is basically modeled as a relay fading channel. So scattering and diffraction causes multipath propagation. Because of the multipath effects, we have fading nature of the received channel, and that fading is being modeled as the relay fading channel. The channel with a random gain, and the random gain is basically nothing but G. Therefore, the total received power is G times P, where G is the gain of this random. Further, if we look at the noise power, the noise power is equal to sigma square. Right, so we say that the system is in a deep fade, that is, there is a fading channel, and the system is in a deep fade basically when the received signal quality is so poor that communication is not possible. And when does this happen? This happens when the received signal power is below or comparable to the noise threshold. So the noise threshold is sigma square, the received signal power is G times P. So my system is in a deep fade. So the system if the signal is below so the system is in a deep fade if the signal level is basically below the noise floor. What does that mean? The signal level is below the noise floor. That means basically the received power G G of P if it is less than or equal to sigma square. So this is the signal power. This is the noise power. If the signal power is less than or equal to the noise power, basically the signal power is less than or equal to the noise floor, then we say the system is in a deep fade. That means this implies that G is less than or equal to sigma square by P. Sigma square by P is nothing but 1 over SNR. So therefore we say that the system is in a deep fade basically if the wireless channel gain, what is this G? G is basically, this G is the gain of the fading channel. If this G, gain of the fading channel, is less than or equal to 1 over SNR, then the system is in a deep fade. Now can someone tell me what is the probability that G is less than, so what is the probability of deep fade? Probability is equal to, basically probability that G is less than or equal to 1 over SNR. Can someone tell me how can I calculate the probability that G is less than or equal to 1 over SNR? Is my question clear? I am saying the probability of deep fade is basically the probability that G, the wireless channel gain, is less than or equal to 1 over SNR. Therefore, can someone tell me how can I calculate this probability? What is the probability that G is less than or equal to 1 over SNR? How can I calculate this quantity? Can someone tell me how I can calculate this quantity? Probability G is less than or equal to 1 over SNR. Okay, PSG, I'm getting the answer. PSG has given the correct answer. Can someone else tell me how to calculate the probability that uh, uh, the gain G is less than or equal to 1 over SNR? What is the probability that G is less than or equal to 1 over SNR? In PhD college, I am getting the answer. Can someone else also respond? What is the probability that G is less than or equal to 1 over SNR? So what is the probability that G is less than or equal to 1 over SNR? See, we have the distribution of G. The distribution of G is exponentially distributed, right? So G is exponentially distributed. So G is exponentially distributed. So that gives you a hint. So given that G is exponentially distributed, how can I use this fact to compute the probability that the probability of G is less than or equal to 1 over SNR? How can I use this distribution to compute the probability that G is less than or equal to 1 over SNR? Uh, so PSG college, I think they have already given me the answer, but I'm just trying to see if someone else can respond with the answer. The distribution of the gain is e to the power of minus g. What is the probability, or how can I compute the probability that g is less than or equal to 1 over SNR? Okay, I think getting the answer, let me go ahead. I think the probability, basically I have to integrate e to the power of minus g. That is basically I have to integrate e to the power of minus g. The probability g is less than or equal to 1 over SNR is equal to basically integral 0 to 1 over SNR e to the power of minus g dg, and this is basically equal to, can someone, what is value, integral e to the 0 to 1 over SNR e to the power of minus g dg, what is this value? What is integral 0 to 1 over SNR e to the power of minus g dg? Can someone tell me what is this value? E to the power of minus g dg from 0 to 1 over SNR. Yeah, I'm getting the correct answer. That is 1 minus e to the power of minus 1 over SNR, which is approximately equal to, 1 minus, see, at high SNR 1 over SNR is small, therefore e to the power of minus x is 1 minus x approximately at high SNR, therefore this is approximately equal to 1 minus 1 minus SNR. Thank you. Both UIET and PSG college have got the answer. That is 1 minus 1 approximately equal. So because e to the power of minus 1 over SNR, what type of approximation I'm using? I'm using the approximation that e to the power of minus x approximately equal to 1 minus x if x is close to 0. That is, if x is very small, or I'm sorry, if if x is very small, then e to the power of minus x is approximately equal to 1 minus x, and therefore this 1 minus e power minus 1 over SNR is approximately equal to 1 minus 1 over SNR is equal to 1 over SNR. Therefore, what we see, interestingly, if you look at this 1 over SNR, now look at this. What is this 1 over SNR? This 1 over SNR is the probability. This is what we say. This is the probability of it. If you look at this, we are saying this is basically the probability of effect. And let me go a little bit back. Let me go to what we said in the very first slide. If you go back to the first slide, what we said is this 1 over SNR, look at this again, this 1 over SNR is nothing but the bit error rate. 1 over SNR, this is the DER. Right. So what we are seeing is something very interesting. What we are seeing is in the wireless communication channel, the bit error rate is basically equal to the probability of deep fade. That is, in a wireless channel, is equal to the probability this is equal to, in the wireless communication channel, the bit error rate is basically equal to the probability of deep fade. So what this is saying is something very interesting. It is saying basically this is a wireless communication system, and therefore the communication is over a fading wireless channel, and the received signal power is varying as a function of the channel gain. Now if the channel gain is high, that is if the channel gain is such that the received power is greater than the noise threshold, then that is fine, there is no problem. But if the channel gain is lower than the noise threshold, or is less than 1 over SNR, or GP is less than sigma square, or G is less than 1 over SNR, then basically the channel is in a deep fade. And when the channel is in a deep fade, basically we are not able to recover, that is the probability of bit error is very high. Therefore, what is the bit error rate? The bit error rate, that is the probability that the bit is in error, is exactly equal to basically the probability of the deep fade event, and the probability of the deep fade event in 1 over SNR. So whenever the channel is basically going into a deep fade, because of the multipath propagation, because of the destructive interference that is arising due to the multipath propagation, basically the bit error rate, all the bits corresponding to that event are lost, and therefore the bit error rate, the probability that the bit is in error, is basically equal to the probability that the channel is in a deep fade. I hope this is clear. What we are saying, let me just repeat it a little bit, because this is important. What it's saying is something interesting. It is saying basically the channel is inherently a fading channel, and therefore there is a certain probability that it is in a deep fade. That probability is 1 over SNR, that it is basically it's basically inversely proportional to SNR. And whenever the channel is in a deep fade, we are losing the bit error rate is extremely high. We are losing basically almost all the bits to error. Therefore the bit error rate, the probability of bit error, is basically equal to the probability that the channel is in a deep fade event. So the significant event in a wireless communication system is the deep fade event. The deep fade event basically says that uh, the received signal power is lower than the noise threshold. And what is the probability of that deep fade event? The probability of a deep fade event is 1 over SNR, which is also basically equal to the bit error rate of the wireless communication system. I hope that part is clear. And this is an important aspect of wireless communication channel, which is what is the deep fade, what is a deep fade event in a wireless communication system, and how is it related to the bit error rate. This says that the probability of a deep fade is actually identical, is actually equal to the probability of the bit error, or the bit error rate in a wireless communication system. So now the main problem, as we have seen, is basically wireless communication system. The main problem is arising due to the fading and the deep fade events. The problem in a wireless communication system, the high bit error rate problem in wireless communication is basically, the problem is basically the deep fade, that is the disruption of communication in a deep fade, that is when the received signal power is lower than the noise power. This is the problem in the wireless communication symbol. So we have to overcome, we have to devise innovative technologies to overcome this problem of high bit error rate due to the deep fade event. So basically the aim of a wireless communication system, the aim in wireless communication technology, so the aim of wireless system is to overcome this problem of deep fade. The aim of a wireless communication system, therefore the aim of designing this new wireless technologies is to overcome this problem of deep fade, to decrease the bit error rate, to reduce the bit error rate. And therefore, as we have already seen, if because the bit error rate is nothing but the probability of deep fade, if the probability of the deep fade, or the probability that the system is in deep fade, if that probability, if we are able to reduce that probability, that is basically if we are able to improve the signal to noise power ratio at the receiver, then automatically the bit error rate is going to come down. Therefore, we would like to basically decrease the probability of deep fade or improve the signal. That is, we would like to decrease the probability that the system is in a deep fade. Basically, what does this all boil down to? We would like to decrease the probability that the system in so what was our aim in wireless communications? We would basically like to design innovative technologies, or like to design newer systems, basically with the aim of decreasing the probability of the deep fade. If I reduce the probability of deep fade in this wireless communication system, then naturally the signal to noise power ratio at the receiver that improves, and therefore if the signal to noise power ratio at the receiver that improves, then naturally the bit rate in a wireless communication decreases. So basically, if I have to represent it by a figure, as probability of deep fade decreases, SNR at receiver improves. If SNR at receiver, if that is improved, then automatically probability of bit error, or basically my bit error rate, this is the aim of the wireless communication system. So the aim of the wireless communication system is I would like to basically decrease the probability of deep fade of the wireless communication system, which implies that the SNR at the receiver improves, which in turn implies basically that the probability of bit error decreases. This is the main methodology, or uh, this is basically an overview of what is the design strategy. So I would like to say this is a design strategy, or this is a design goal, a design strategy, or design goal of so this is basically a design strategy or a design goal for the wireless communication system. I hope this is clear. If there are any questions, you can ask me. If there are any questions, please let me know on the chat window if there are any questions. At this point, I will just wait for a minute over here before I go on to the next topic. I will just wait for a minute over here. If there are any questions, please let me know over the chat window if there are any questions. Anyone has any questions? Okay, so in that, let me go on to the next topic of the wireless communication, which is basically multiple antenna systems. As you might know, multiple antenna systems, that is multiple antenna technologies. Let me go to the next topic, that is as many of you might be aware, multiple antenna wireless communication is one of the latest technologies or one of the latest advances in wireless communications. That is multiple antennas, that is communication using multiple antennas is one of the latest advances in a wireless communication system. So let me write it down. So communication As many of you must be well aware, communication using multiple antennas, that is either multiple transmit antennas or multiple receive antennas, that is one of the latest advances. That is one of the latest advances in a wireless communication. In a wireless communication system. Right. So what does that mean? That means that either I have multiple antennas at the receiver or I have multiple antennas at the transmitter. So basically if I have multiple antenna wireless systems, I have multiple antennas either at the receiver or transmitter, or I have multiple antennas at both, at the receiver and transmitter. Okay, I'm getting a question from GCT. What is the difference between symbol error rate and bit error rate? See, symbol error rate is basically the probability that the transmitted symbol is in error, but the symbol comprises of many bits, right? Because there are several bits that are transmitted in one symbol. So the bit error rate is basically what is the probability that a single bit, any given bit, is in error. For instance, let us say I am transmitting in 16 QAM. In 16 QAM, then I am transmitting log 16 to the base 2. That is 4 bits per symbol, right? So what is the probability of bit error rate? The probability of bit error rate or probability of bit error or bit error rate is basically the probability that one bit is in error, right? The probability of symbol error or the symbol error rate is the probability that one symbol is in error. Symbol is in error basically if any one of the bits is in error. So that is the relation basically between bit error rate and symbol error rate. Symbol error, basically speaking, bit error rate is basically the probability that the bit is in error. Symbol error rate is the probability that the symbol is in error. However, since in BPSK modulation we are transmitting 1 bit per symbol, that is it's either plus or minus square root of p, which means there is 1 bit per symbol. Therefore, for whatever we have considered so far, the bit error rate is equal to the symbol error rate. I am getting another question: what is the significance of the SCR performance? See, the symbol error rate has a significant impact on the performance. If the symbol error rate is high, then basically communication is not possible, because communication basically depends on reliably transmitting information from the transmitter to the receiver. Therefore, if the symbol error rate is high, then the quality of communication is poor, right? Also, I am getting a request for the textbooks. Textbooks are basically, as I already mentioned, the list of textbook is given in the document that has been uploaded. Kindly refer to the document that is basically been uploaded in the documents section. If they are not able to find that document, there is a PDF document. Kindly contact the support. It should be, the document is available in the The document is available in the list of document, the document section of this course. Alright, kindly refer to that. There is a list of textbooks that is available regarding this feeding wireless channel and bit error rate of the feeding wireless communication system. Now I'm going to a multiple antenna wireless communication system. Let us improve our system. Let us say I have two receive antennas and one transmit antenna. I'm going to consider a system with two receive antennas and one TX. That is, previously I had a single receive and single transmit antenna. I am now making my system as basically two receive antennas and one transmit antenna. So what I'm saying is now I'm going to consider a system with two receive antennas and one so this is my receiver. I'm also going to denote this by Rx. This is my transmitter. I am also going to denote by Tx. So now what I am saying is, instead of a single antenna at the receiver, I have two receive antennas, right? So whatever is the signal that is basically transmitted by the receiver, it is received at the two receive antennas, right? Previously we had y is equal to, we had only one received signal y. Now we have two received signals. We have y1 and we have y2. So previously, remember, we have one transmit signal x, right? Previously we had only one received signal y. But now because we have two antennas at the receiver, we have two received signals. That is, I have y1, y2 corresponding to the two antennas. Therefore, now I can write my system as y1 is equal to h1 x plus n1 n1, y2 is equal to h2 x plus n2. Right, because I have two receive antennas, I have two received signals. Therefore, what am I saying? I'm saying y1 is the signal, this is the signal this is the signal, y1 is the signal received at receive antenna 1, y2 is the signal received at receive antenna 2. So I am saying basically y1 is the signal that is received at receive antenna at the receive antenna 1. y2 is the signal that is received at the receive antenna 2. Therefore, we have y1 is equal to h1x plus n1. y2 is equal to h2x plus n2. What is h1? h1 is the coefficient corresponding to receive antenna 1. See, previously we had one coefficient, one Rayleigh fading channel coefficient. Now we have two Rayleigh fading channel coefficients. What are the two Rayleigh fading channel coefficients? This coefficient corresponding to receive antenna 1, this is h1. This coefficient corresponding to receive antenna 2 is h2. Therefore, I have y1 is equal to h1x plus n1. y2 is equal to h2x plus n2. Therefore, I have y1 is equal to h1x plus n1, y2 is equal to h2x plus n2. I can also write this a vector. I can write y1 y2 vector is equal to h1 h2 times x plus n1 n2. So the received vector, that is basically the received signal vector, what we are saying is now we have two received symbols across the two antennas, that is y1 and y2. Therefore I have a vector, basically I have a vector comprising of y1 y2, which is equal to h1 comma h2 into x. The h1 h2, that is the vector h1 h2 times x. So this is now the channel vector, right? This is now the channel vector plus the noise vector. Thus this is now the Therefore, now I have a vector model for the communication system. Therefore, now I have a vector. Therefore, because I have two receive antennas, therefore we have a vector model. Because we have two receive antennas, therefore we have a vector model of the wireless communication system. Why do we have a vector model? Because now I have two receive antennas. Therefore, I have two signals y1, y2. If I put them together as a vector, I have a vector communication system. Right? So y1, y2 channel vector y. In fact, I can call this as vector y bar is equal to h bar times x plus n bar. That is vector y is equal to vector h times x, where x is the transmitted signal plus n bar, where n is the noise vector. Right? Okay. Further, we are going to assume the following thing. We are going to assume, which is reasonable, and further the different noises n1 and n2 are independent. So we are going to assume each noise n1 comma n2 of power sigma square, and the noises are independent, that is expected value of uncorrelated, that is expected value of n1 n2 or n1 n2 conjugate is equal to 0. That is basically these noises are equal power sigma square, and the noise at the different antennas, they are independent. Therefore, now what I am going to do at the receiver is I have two signals y1 and y2. I am going to combine these two signals, right? As simple as that. So at the receiver, we combine the two signals y2 at the two receive antennas. So at the receiver, what do we have at the receiver? At the receiver, we have to combine the signals of the two receive antennas, that is y1 and y1 and y2, which are received on the two receive antennas. Therefore, let me choose the combining weights w1 w2. At the receiver, we perform w1 conjugate y1 plus w2 conjugate y2. Right, so basically I am using weights w1 and w2 to combine the signals y1 and y2 at the receiver, that is I am performing a weighted combination, that is W1 conjugate Y1 plus W2 conjugate Y2 at the receiver. This is also basically I am performing a, what is this? This is performing a weighted combination. This is also a so basically I'm using the combine, I'm using the combiner, I'm using the combining weights W1 conjugate, W1 and W2 to basically perform W1 conjugate Y1 plus W2 conjugate Y2, which is basically using the weights W1 and W2 to combine the signals Y1 and Y2 which are received on the two receive antennas. Therefore, what I have here, I can represent this as, I can represent this mathematically in vector notation. I can represent this as W1 conjugate Y1 plus W2 conjugate Y2. This is equal to W1 conjugate W2 conjugate Y1 comma Y2, which is also equal to, now you can see this is basically W bar Hermitian Y bar, where W bar is the vector, W bar is equal to W1 W2, and Y bar, of course we know Y bar is the vector Y1 Y. What we are saying is the following thing, basically we are writing it using a vector notation, right? So we are basically using the vector notation. So we are saying W1 conjugate Y1 plus W2 conjugate Y2, which can be used representing the vector notation as W bar Hermitian Y bar, where W is the weight vector. Alright, so W is the weight vector, that is W1, W2, Y is the vector Y1, Y2. So to do a brief recap, what we are doing is basically we have two signals. We have two receive antennas. We have a multiple antenna system. In this multiple antenna system, we have two receive signals, Y1 and Y2. Right? And one transmit signal X. Therefore, now these two, we have to combine these two receive signals. And therefore, what we have to do to combine these two signals Y1, Y2, we are performing the weighted combination W1 conjugate Y1 plus W2 conjugate Y2, which can be represented using the vector notation as W Hermitian Y bar, where W is basically the vector W1 conjugate W2 conjugate, which is nothing but W Hermitian times vector Y1 Y2. So I have W bar Hermitian Y bar. Right? So this is the combiner. This is a linear combiner. Also, this is also known as a linear combiner. Yeah, I'm getting a question from PSGCT. What about the assumption of noise? That is correct. We said the noise is Gaussian noise of variance sigma square. Correct. We said the noise is Gaussian noise, so that noise is additive white Gaussian. But now in addition to white assumption, that is that each noise is temporally independent, we are also assuming the noise is spatially independent, because look at this, we have said expected N1 N2 conjugate is 0. That is the noise across the two antenna elements is independent. So the noise is both temporally independent and is also spatially independent. So this is spatio-temporally white noise. Alright. So thank you. That's a good question actually. It's a good point. Alright, so let us stop here. So we have basically started with a multiple antenna, introduction to a multiple antenna wireless communication system. Next lecture what we are going to see is basically we are going to complete setting up this model for the multiple antenna wireless communication system, and also analyze what is the performance of the wireless multiple antenna performance communication system, thereby illustrating what are the performance gains, that is what is the improvement or what is the advantage of a multiple antenna system versus a single antenna system. Alright, so let us stop today's lecture here. Thank you very much.